Hey John, if it's possible, can you go a bit slower? Because sometimes you go a bit too fast and it's like you're
A bit
writing down.
slow. I will do my best. Interrupt me. Let's have some interaction.
But then you can't hear them.
I don't need to follow.
You do.
I only wish I could be in the classroom with you, then you could control me better.
Jason, thank you for suggestions that students with zero attendance should be called out. But trust me, I'm sending emails, but zero reaction. You're ignoring my emails. Okay, anyway, let's start. John, the class is yours.
Yes, okay, thanks, Tatiana. I'll wait for a couple of minutes. Anybody joining up until 10, 10:05. Right. Okay, guys, it's 10:05. Happy Chinese New Year to any Chinese amongst you and anybody else who wants to celebrate it. But I'm afraid we've got to work today. Right, just a recap on the last lecture. And please interrupt me if you have any questions or if I'm going too fast. We were looking at image enhancement. And this is achieved using two image processing operators, which is image shift and the second one is image multiply. And the way we employ this method is to first of all obtain the histogram of the original image. Now remind you, what is a histogram? It is a graph. It is a record of the number of pixels at each intensity in the image. Now for exam questions, you would have 4-bit resolution per pixel, which means the values of a pixel in a 4-bit resolution image can be between 0 and 15. I don't have to explain that to you, surely, because in binary it's going to be 0, 0, 0, 0 to 1, 1, 1, 1, the range over 4 bits binary. And the histogram is a graph. Offset it because you will have values at 0. And the vertical is the number of pixels. And the horizontal is the intensity. And the intensity is the value of the pixel, the brightness value of the pixel, which will go from in a 4-bit resolution image 0 to 15, and 15 is usually regarded as W for absolute white, 0 is B for absolute black. And you will find on an image, we will get a range of pixel values. So we might get a histogram that looks like this. And these, for example, this might be intensity 3, and this would be the number of pixels in the image that have intensity 3. On that histogram, you can define the minimum gray level, and again, we're applying this to gray level images. You can apply it to color, to the RGB, or better still, the intensity, if you're using intensity, hue, and saturation coding. But let's stick to gray level images, and the minimum pixel value is Gmin. The maximum pixel value is Gmax. And by a process of shifting that histogram, the first step is a shift G
Hi, it looks like there is a problem with connection, network connection for the John. Please bear with us. I'll try to investigate what's going on. So you have a mini break now while John is trying to join in. Okay, you're in now.
Right. Let's see if I can share. Share application screen, application window.
You need to find out where you stopped because when I called you, you were already 3-4 minutes.
Yeah, hang on. Why can't I share my? Oh, I've lost my whiteboard, have I? Oh.
Okay, you're sharing your whiteboard.
Right. Oh, that's the wrong one. Yes, let's find the one I want.
Okay, good. I'll take up.
Just hang on. Just hang on.
Okay, good luck.
Still not there. Oh. Oh, I'll grab a new whiteboard. It's easiest. You got that? Hello?
Yes, we are getting there.
Right. Sorry about that, folks. I have no idea what happened. It sounds as if I was lecturing quite happily to myself. Can somebody tell me what was the last thing you heard?
Can you speak up, please? Shift G minimum by intensity map G max.
Right. Okay.
G
Histogram.
min, G max. This is what we said.
Yeah. Okay. I was talking about problems of using the enhancement algorithm. And the problem is, in a real system, there will be faults on your CCD array. It will mean that when you get the histogram of the original image, you would expect the image, these would be the histogram entries. I'll draw it as an analog function, but it is digital. One would be expecting a G min and a G max, which are the limits of the intensities in the original image, but there will be some pixels at 0 and there will be some pixels at W, and these are due to faults on your CCD array. And every imaging system will have some faults on the array. Your latest iPhone, 16 megapixels, not all of those 16 million pixels will be working. And if we get one stuck at 0 fault, it will give me an intensity at 0. If we get one stuck at 1 fault, we would get an intensity at W, which means that G min in the original histogram would be 0, G max would be W, and the algorithm will not change the image at all. So what you have to do is you have to estimate G min. And G max. So supposing we have a histogram of the original image, and supposing it goes something like this, and this would be the intensities. Let's draw them as remember they are. Here I've got intensities at 0, and here I have got intensities at W. And what you need to do is you have to decide yourself by observation, choose G min and choose G max. G min in the initial histogram cannot be 0, G max cannot be W. And in real systems, Supposing you have a CCD system operating in Brunel University and they're looking at the cameras and it's nighttime and you want to actually see information in the image. Now, if you have a system where Gmin and Gmax can be variables, you can actually choose in real time to set Gmax and Gmin, and the enhancement will give you an enhanced image between those ranges. So by adjusting Gmax and Gmin and looking at the enhanced image, you can get and choose the best quality of image to interpret what you're looking for. Now, having said that, just changing Gmax and Gmin is a simple operation on the interface, but there's an awful lot of processing has to be done to actually change the image. Because remember, real images are high resolution. I think that's all I want to say with the enhancement. Now for something new. Hope you're still with me. We've been dealing with single pixel operators so far. They're sometimes called monadic operators, and that gives us our enhancement possibilities. The second class of image processing I want to look at is 2-pixel operators. And these are often called dyadic operators. And the basic idea of a 2-pixel operator is you have 2 images. Let's call that image A. And we have image B. We extract a pixel from image A. Let's call that Aij. And we have a pixel from B at the same location, Bij. They are inputs to your function, and the image processing function in general excuse me, is a function of Aij, Bij. And that produces an output, and that output goes to the output image, which gives a pixel, let's call it C, at the same location as the input from A and the input from Bij. So that is a dyadic, or more simply a 2-pixel operator. Involves 2 input images and produces a single output. And this is used mainly for special effects. But it sometimes has uses with real image processing. The obvious thing is image add. Adding 2 images together. And you may well think it's so simple, it's so obvious. If you're adding 2 images together, the output pixel Cij equals Aij plus Bij. And if you've written that down or got that in your notes, no. It's slightly more complicated than just adding pixels. And the reason is Cij, if I use this equation, has the range naught to 2W. And this will happen if Aij and Bij are both absolute black. Adding them together, it will be an output pixel absolute black. But if Aij is absolute white, W, and Bij is absolute white, we get 2W, which is out of the range of the image system. And remember, W is equal to 2 to the n minus 1, where n is the number of pixels. So for 4 bits, W is 15. And for real systems, which are 8 bits, W is going to be 255. Right, so instead of doing a simple addition, we have to apply a correction factor. And it's a simple one. And the algorithm for adding two images, Cij equals Aij plus Bij divided by 2. And that is the image add algorithm. Right, that's a relatively straightforward operator. If we've got image addition, there is image subtraction. And initially, you might think image subtraction is Cij equals Aij minus Bij. Again, no, it's not as simple as that. The range. Cij must be in the range 0 to W, the resolution of the imaging system. But if Aij is absolute black, which would be 0, and Bij is absolute white, then the Cij would appear to be minus W. It's outside the range. If Aij is absolute white and Bij is black, then Cij, if I use this equation, is going to be plus W. So we have at this stage a range. Cij is greater than or less than or equal to W and greater than or equal to minus W. It needs to be brought into range of the imaging system 0 to W. So the correction factor Cij equals Aij minus Bij, which will have a range of minus W to plus W. Add white to it. That now takes the range of, it was minus W to plus W. This will now be 0 to 2W. We want to bring it in the range 0 to W, divide by 2. And that is the equation for image subtract. Again, it has to be applied to every pixel for all values of Ij. Right, a couple more dyadic operators. Image maximum. This is a way of combining images, and it is Cij equals Aij if Aij is greater than Bij, else it equals Bij if Bij is greater than Aij. And of course, there could be a situation where they're both equal, so one of these can be greater than or equal to. Let's have the bottom one there. So there's no problems with the image max. And the other one is the image min, which is again simple. Hope you're still with me. Right, image minimum is going to be Cij equals Aij if Aij is less than Bij. Otherwise, it equals Bij if Bij is less than Aij. In other words, you pick the two inputs. For the maximum, you pick the brighter pixel of the two. For the minimum, you take the darker pixel of the two for comparisons of corresponding pixels across the whole image. And again, if they're equal, have one go to, in this case, Bij. Right, so those are dyadic operators, and they're not particularly important, but I've included them in there. If you come across them, you know what they are. Now we come to more important operators, the third class of image processing operators, which are window operators. And the schema for a window operator: take an image, and instead of taking a pixel from the input image, you take a window of pixels. I'll draw it rather large. The shape of the window can be any shape. 3 by 3 is quite common, but it could be larger, it could be smaller, it could be a line, it could be vertical, it could be horizontal. And the key thing, this is image A. The central pixel is Aij. And that whole window goes into a function. I'll just draw brackets for the function. So the whole window is connected to the function. It produces a single output, and that output goes to an output image. And the output is called B. This will be Bij. It produces an output corresponding to the center of the window. So there's a scheme, a window coming in and a single pixel going out. Now, the first thing to notice is the output is smaller than input. Why? Because when the window is fitted in the top left-hand corner, the output will correspond to the center of the window. We will lose the top row and we will lose the left-hand column. And the same will be true for the other corners. So we actually lose top and bottom row and left and right column. Which means if you have an exam question, a 5 by 5 input results in a 3 by 3 output. And if this is an exam question, this will be the size of images you will be dealing with. So don't worry about the loss of the edges. It is devastating at very small images, but you will never use this in practice with small images, apart from demonstrating the method in exam questions. For real images, if the input size is 4,000 by 4,000, the output will be 3,998 by 3,998, and you won't notice it. And if you really want to restore it back to the original image, just repeat the edges on the filtered image to make up for the columns and rows that are lost. So that's not a big issue, but beware of that. In exam questions, if you have a question on filtering, the output image will be smaller than the input image. Right, the first window operator, low pass filter. And it is sometimes called smoothing. How are we doing for time? I've got another 20 minutes, that's good. The window operator for a low pass filter is very simple. 3 by 3 window. And the constants, the weights in the window, they are all 1. So it's hard to not remember the image. Now I'll use an example. An example of low pass filtering. Let's take an image, and I'll take a 5 by 5 image. You don't have to copy this down exactly, you can devise your own. 1, 2, 3, 4, 5. And let's supposing the coefficients are 0, 0, 0, those are black. Let's have the whole top row black. Let's have 0, 0, 0, 0, 12. Let's have 0, 0, 0, 15, 15. We're bright there, then 2, and the rest can be absolute white, 15. Now, if you were asked to describe that image, it would clearly be a black region at the top left and a white region at the bottom right, and clearly there's going to be a division between the black and the white there. So it's a top triangle black and a bottom triangle white. And we are going to low pass filter this. So in filtering it, we will produce a 3 by 3 image. And the first operation of the window, let's see if I can get a green pen. Oh, no, don't go away. The window operator, here it is. Will initially set on that position. And clearly the image is all zeros. Weighting it by this, the output will be 0. I now move the image to the next position. He's sitting in there. The center pixel will correspond to here, and I will have all zeros apart from this bottom one, which will be 15. Now imagine the window is shifting. If I draw all the positions, it will become messy. When the window is in the top right-hand corner, it will be covering 0, 0, 0, 0, 0. 15 plus 15 is 30, plus 12 is 42. Don't go away. Now we move the image down to the window down to the second row. So the window will now be in this region. And it is going to be 0, 0, 0, 0, 0, 0, 2, 15, 15. That is going to be 32.
So John,
Moving. Yes.
do you basically add everything that's within the window?
Yes, you are. What you're doing is 1 times the pixel plus 1 times the pixel. So you add everything in the window. It's as simple as that, okay? In the middle, 0, 0, 0, 0, 0, 15, 30, 45, 60. Middle right, 0, 0, 12, 0, 15, 30, 42. Gosh, my arithmetic. 42 and 45 is, gosh. 1, 2, 3, 4, 5 15s are 75, and 12 is, I think it's 87. Now down the bottom, 2, 15, 30, 60, 75, 77. Check these values. I might have got some wrong. The method is correct, but the arithmetic might be wrong. Now sitting in the bottom middle, there's going to be 1, 2, 3, 4, 5, 6, 7 at 15. I think that's 105. And finally, the bottom right, they're all 15 apart from the 0 there, and that's going to be 120. So that would appear to be your filtered image. But we've got some crazy values appearing in here. 0 and 15 are within the range. All the rest are outside the range. Now, clearly, this has to be normalized. We need a correction factor. And the correction factor has got to bring the range of the output into the same range as the input. So the input is 0 to W. The output, well, clearly 0 is going to be the minimum value. And we've got an example there. The maximum value would be, well, it doesn't occur in this image, but if all the pixels under the window were 15, it would be 9W. So the correction factor, if I've got a range 0 to 9W, I want a range 0 to W, divide by 9. So the algorithm is the window, the unit weights, 1, 1, 1, 1, 1, 1, 1, 1, 1, and you have to divide by 9. Or you could assume the weights were 1 over 9, both the same. So if we now take this raw filtered image, if I now divide each of these by 9, and remember the pixel has to be integer. We have 4 bits integer for the pixel value, so we may have to round it up. And so taking that down, can I keep the same on the same screen? Yes. So applying that now. Naught, obviously divided by 9 is going to be 0. 15 divided by 9, it is 1 with the remainder 7. That will round up to 2, I think. 42 divided by 9, I think that's going to round up to 5, or round down to 5. 32, well, 4 9s are 36. I think 4 is the closest. 60, I think 7 is the closest. 87 is going to be 10, I think. 77, I think, is going to be 9. 105, I think, is going to be 12. And that is going to be 13. So there we now have our low-pass filtered image. Now, if we can compare that with the original, let's take the original from the center of the image, because that is the area where the operator has been looking at. Remember, we lose the top and bottom row and the sides. So if I now take the center of this image, which will be, I'll draw it on here if I can, which will be this region here, we can see the effect we've had. In the original image, extracting that from the input on the 3 bits going back, it was 0, 0, 0, 0, 0, 15, 15, 15, 15. 0, 0, 0, 0, 0, 15, 15, 15, 15. Now the appearance of that is a white top and a black top and a white bottom. After filtering, we get this image. This is comparing pixel for pixel. It's going to be 2, 5, 4, 7, 10, 9, 12, and 13. A much more gentle change from black to white. Goes through a grey region. Yes, the top is still the brightest, darkest, and the bottom is still the brightest. But if you were actually looking at this, this would be a much smoother image. So there is a smoothing algorithm, a filtering algorithm for low pass. So, any questions on that? Right, let's move to the next one. I can just about start the next filter. If there's a low pass filter, guess what? There's a high pass filter. There's a number of them, but the simplest is a window operator. Same type of operation, but the coefficients are different. And in the high pass filter, we have coefficients -1, -1, -1, -1, miss out the middle for the moment, -1, -1, -1, -1, but the center is +8. And it's interesting to note the sum of the coefficients is 0. It's known as a balanced filter. Right, exactly the same initial process. Okay, so we correlate this with an image and we will produce an output picture. And I want to look at the range of values on the output. Right, we'll take this window. If I'm correlating it with an image where all the output pixels were white and all the center pixel was black, let's draw the image. Supposing the window was over this image. Where the center is absolute black and the output is the outer rows and columns are white, we would have -1W, -2W, -3W, up to -8W. The center is 0, absolute black. 0 times +8W is 0. That would give a response of -8W. If I now take the extreme opposite of this image, where I've got black around the outside, absolute black, and white in the center, the response is going to be plus 8W. Why? Because the outsides are black, 0, times -1s will all give me 0. The center is white, W. It's weighted plus 8. It gives me 8W. So the overall range is the output pixel, let's call it Bij, is greater than or equal to 8W and less than or equal to -8W. So it's got to be normalized the same way as in the same way as the low pass filter image has to be normalized. But we might think, and one way, I won't write this down because this is what you don't do, but it might occur to some of you, if we want to bring this in the range 0 to W, if I were to add 8W to this Bij pixel, it would then have a range of 0 to 16W, and then divide the whole thing by 16, we would be down to 0 to W. So that is a possibility, but it won't work, and it won't work for the same reason that we had with the image enhancement. There will be pixels stuck at white and stuck at black on any imaging system. They never work perfectly. The other issue is if we were doing high-pass filtering to enhance an image for human consumption, these two images here, where you've got a single black pixel in a white region or a single white pixel in a black region, you wouldn't be able to detect those as humans. They would be insignificant visual features of the image. So if we were to normalize from -8W, +8W to 0 by 16 by the shift and divide method, we would contract and compress the filtered image into a very narrow range of pixels. So instead of normalizing this by shift and divide, we need to normalize the histogram of filtered image. So, don't you despair. Come on. So having filtered the image, and the histogram of the raw filtered image, this is number and this is intensity. And because we have so many negative weights in the window, chances are we will have negative values on the filtered image. And so we would have our histogram, which could have negative and positive values. This would be -8W, and there would be some pixels due to faults on the array stuck at -8W, and there would be some pixels stuck at +8W. And these would be ignored. determine the G min and determine the G max, and you normalize that histogram using the standard normalization procedure. So the shift to 0, K would be minus G min. And of course, if G min is negative, we will be adding G min. So we would shift the histogram in that direction to 0. Then having done that, the multiply is going to be, the multiplication factor constant will be W over G max minus G min, exactly the same as we did for image normalization. Having done that, you get the pixel update table and you get the filtered image. Right, we are getting to a stage where these algorithms actually do need computer support because of the amount of data and calculations. But if you understand the methods, then I'm sure if they come up, a verbal description, a correct decision of the methodology will gain you the marks if indeed this becomes a question. Right. Another problem with high-pass filtering. How are we doing for time? Gosh, I'll run out of time. I'll have to leave that till next week. So that's the high-pass filtering strategy. It's 4 minutes to 11, so I've got to finish now. Any questions? Silence. Okay, next week I will finish off the high-pass filter, and then we move on to the last class of image processing algorithms I want to look at, and this is double window operators, and this leads to edge detection strategies, which are quite important in image processing and interpreting data, AI and all that. So that's where we're going next week. Any questions? Okay, have a good day, folks. Sorry about the dropout early on. I hope you've got the majority of the lecture.